increase in road safety, productivity, efficiency of parking space usage, a reduction in traffic jams and environmental pollution, and the allowance for greater independence are some of the benefits which a proper implementation of a level 4 self-driving car will allow. It is therefore something that we must definitely pursue. The objectives of our project can be divided into two main sections: the simulation, where we will handle both structured and unstructured environments mentioned, and the robot implementation, where we will implement some simple scenarios to test our system in real time. This is the overall block diagram of our implementation. The global planner plans the global path from the user location to a specified destination. The behavioral planner handles the different scenarios encountered by the vehicle. It was implemented using a finite state machine with 6 states. The local planner creates dynamically feasible, safe, and comfortable paths along the global path. The collision checker checks for collisions in these paths and selects the best path. The velocity planner creates a velocity profile for this path and outputs a trajectory. The controller follows this trajectory and completes the process. The parking module was implemented separately using an optimization-based approach. Moving on, let's take a look at the capabilities of our implementation in a structured simulated environment. Intersection handling was covered, and as you can see, the ego vehicle was able to move through that intersection with general ease. The ego vehicle is approaching a vehicle in front of it. It slows down and is able to maintain a safe distance, all while following the lead vehicle. Here, we will look at a scenario where a vehicle cuts into the path of the ego vehicle. The ego vehicle is able to give way to that vehicle and maintain a safe trajectory with no collisions. Let's take a look at some scenarios in the highway where the speed of the ego vehicle is higher. The ego vehicle has the capability of executing overtake maneuvers in a safe and comfortable way, as you just saw. Alright, let's now take a look at how the implementation performs in unstructured simulated environments. The ego vehicle can handle all sorts of jaywalking pedestrian scenarios as shown. It can also drive through dense crowds without any collisions while trying to move forward instead of staying stopped in one position. We will now see an instance where an unruly driver runs a red light. The ego vehicle is able to quickly react and stop without colliding. We have now come towards the end of our journey, and the ego vehicle stops at its destination. Now let's take a look at the parking implementation. We can handle both perpendicular and parallel parking. This is a perpendicular parking scenario with multiple stages. A 1:10 scale Ackermann steering based robot was used for the robot implementation. A USB hub was used for communication, and a VESC motor controller was used to control throttle and steering. A 2D LiDAR and 2 Z cameras were used to map the environment around the robot. An NVIDIA AGX Xavier was used to process the data from the sensors and to provide control to the wheels of the robot. We will now demonstrate a static obstacle overtake scenario implemented on the robot. The state machine of the robot is shown on the right hand side of the screen. It is a simple version of the state machine implemented for the simulation. The robot is able to successfully execute an overtake maneuver as shown and come back to the follow lane state. In conclusion, we have been able to achieve level 4 autonomy in a simulated environment in both structured and unstructured scenarios in a Sri Lankan context. A robot implementation was also demonstrated to test the functionality of our system.